first method is a way to approximate the value of a function. So you have a curve and a point that you know, for example 1, 1 or f of 1 equals 1, and a point that you are trying to find. You also have the derivative. So you have something that looks like this. dy dx equals, but on the other side you have a bunch of stuff like lightning bolts and kitty cats and other crazy gobbledygook, yes, gobbledygook, that you cannot integrate. So let's recap. You have a curve, you have a starting point, which is a point that you know, you have an end goal, the point you're trying to find, and you have the derivative. Well, with the derivative you can find the tangent line at your starting point. The tangent line gives us an idea of what direction the curve is going in. If we find the equation of this line, we can find the next point on the tangent line. At that point, we find the equation of the tangent line again and repeat the process. We now have our approximation. The approximation is not very accurate. This is because of the step size. The step size is how far you move in the x direction each time. The smaller the step size, the more accurate your approximation will be. Since we have our initial point and the derivative, we can use point-slope form to find the equation of the tangent line. Yay! The slope, m, can be replaced by the derivative, and x minus x naught is really the same thing as change in x, or h, our step size. So now we have this messy looking thing that when we simplify turns into the pretty little equation that we will use for the rest of our method. But we still need one more thing, a table. We will use this table to keep track of our x and y values as we move across the curve with our approximation. Now let's use this idea to actually do a problem. If trying to do this problem late at night, a fantastic source of energy is popcorn! Yum! For this problem you are provided with the derivative and an initial condition, as well as the step size. The derivative is dy dx, or y prime, equals x plus 2y. The initial condition is y of 0 equals 0, and the step size is 0.25. The goal is to approximate the value at x equals 1. We can fill in the xn column on our table by increasing x each time by 0.25, our step size. Then, to find yn, we will use our equation that we found for the tangent line. We start this process by finding y1. We know that h is 0.25 and that y0 is 0. The derivative at 0, 0 is 0. So y1 equals 0. So we can put that in our table. Yay! Then the next step is to find y2, which is f of x1 plus h, or f of 0.5. Now we plug that point, 0.250, that we just found, into our derivative to find the next slope. We plug that, our step size, and our previous point into the equation for the tangent line to find the next y value. We find that f of 0.5 is 0.0625, and we add that to our table. All you have to do is keep repeating this process until you get to the value you want. So we have to do it 2 more times.
So you find the slope using the derivative at the previous point, again, which is 0.625, and you use that, and the step size, and the previous y value, and plug that into the equation for the tangent line, again, and find f of 0.75, which is 0.21875, and you put this in the table. And you repeat this process, again, using the derivative, step size, previous point, blah, blah, equation, tangent line, new value, f of 1, da, 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 equals
0.515625. Yay! That's our approximation. Let's compare it to the real value by looking at the graph. Yes, I had this graph the whole time. Shh. It's an under-approximation because the graph is concave up. So remember, first we found the equation of the tangent line at our starting point. Then we moved 0.25 in the x direction on that line. At that point, we found the tangent line again, and moved out 0.25 again, and so on. And that's how we found f of 1. Yay!